Now, let's take kind of one nice example for projection that is going to become very important as we move forward. And this is really understanding in a deeper way what we mean by components versus the actual vector itself in an abstract way. And we've started to do that with the previous example. And this is kind of a fundamental idea. It causes a lot of confusion because we get confused when we start changing our bases and coordinate systems. We're very used to drawing our 3D x, y, z right-handed coordinate system. Why is that right-handed? Because x cross y is z. So you put your fingers on x, you curve into y, and you get z. We are very biased in the world of physics and math. We only use right-handed coordinate systems. Sorry to all you left-handed people. However, I've always pointed out that gives left-handed people an advantage because they're writing with their left hand and they never forget to use their right hand to do the cross product. Right-handed people are taking the test and in panic use their left hand and get the wrong answer. So if you're left-handed, you actually have an advantage that we've picked right-handed coordinate systems. Now, let's just draw a few vectors. I'll draw the vector c that goes to the point 1, 2, 3. I'll draw the vector r that goes to the point x, y, z. And I'll draw the vector a that connects the two. So we can see some nice features from our drawing. We know by our rules of vector addition that c plus a equals r, because we have the head to tail construction, and then we connect the two along r. We could then rearrange this and write this as our vector a equals the vector r minus c. And if we wanted to, we could then write this in components, that the vector a is x minus 1, comma y minus 2, comma z minus 3. Now, the important thing to keep in mind is this notation assumes a certain basis, this set of x, y, z, and it provides us with the components, actual numbers that appear to give us the vector. But the vectors are completely independent of the coordinate system. So I can come in and erase my coordinate system. And this is all true. But you have no idea if this is true. Oh, got to erase my components. Until I draw in a new coordinate system. And that's kind of a key idea. So we will, because what's going to happen is you're very used to geometric vectors. You're used to position, velocity if you're doing physics. What you're not used to is when we suddenly use the vector space of apples, or the vector space of matrices, or the vector space of linear functions, or the vector space with sines and cosines as a basis. As we start getting to these more abstract vector spaces, you have to be comfortable with the idea of, okay, the vectors exist. I have rules for adding them. That's what makes them vectors. But how do I get a basis or component out? Any thoughts, guesses, ideas on how you might find the components of a vector? What is the key mathematical idea to doing this? So talk to the people next to you. You're kind of spread out. Find someone next to you. How do we find components? What is the key mathematical step? I'll give you a hint. It's one of the two most important ideas in the course. So how do we find, given a vector and a basis, how would we find a component? And that's the word we're looking at. We project. It's all about projection. That is the key idea. And it's subtle, but it's important. Because a lot of times we will arbitrarily define what it means to project. But for physical vectors, we know what it means. Right? If I have a vector C and I have another vector R, what does it mean to project C onto R? And you're not allowed to use the word dot product. You're only allowed to use geometric concepts that you can measure. Yeah, what's that called? Drop down the the line that is what? Perpendicular. And how many of you remember your Euclidean geometry? Perpendicular lines is actually something we can construct. With a compass and a ruler, I can make a perpendicular line. Having made the perpendicular line, what is the projection of C onto R? Well, which part, geometrically, which part am I going to measure with my ruler? From where to where? From here, we'll start at here, and to here, right? This is the projection, or C parallel. This piece here is the perpendicular one. And we define that by an operation we're going to call the dot or scalar product. So projection we call the dot or scalar product. And notice in this case we've defined it completely geometrically, and it's actually more than just C parallel. It involves the magnitude of R as well. So the dot product itself is the projection and the magnitude of R. It contains both, which we also will call the magnitude of C, the magnitude of R, and the cosine of the angle between them. Again, things that we can measure. This is the actual definition of projection. This is what allows us to find components for physical vectors. It's not Cx times Rx plus Cy times Ry plus Cz times Rz, because that presumes you knew what the components were already. Right? So you can't define the components in terms of the components. You need an actual operational definition of how you're going to do projection. And for physical geometric vectors, we do projection geometrically by measuring the actual parallel component. That may seem silly to spend a lot of time on and focus, but it's key, because later on we're going to describe things abstractly. We're just going to declare three vectors to be our basis, and we're going to define the dot product in terms of those vectors. So we'll be doing it a completely different way, because we won't have a natural physical definition of the dot product, because it's an abstract vector space that's critical for what we're doing. So you have to understand what we did here, so that when we do it in a very abstract way, it's less confusing. Now, to go even farther, we can now write things like C parallel is R dot C, something we've defined, a projection operation, divided by R. And C perpendicular is basically a vector itself, so we can take C and subtract off the magnitude of C in the direction of R. Right? So R vector over the magnitude of R is a new thing we'll call R hat. Which is a unit vector. So that gives us a direction, because this thing has a magnitude. We do have to define one other notation. The magnitude is just the projection of a vector onto itself. And that defines everything we need to know. Any questions on those? Because now we're going to introduce some abstract notation. So we just said for the physical vector, we have A dot B. And again, by the way, if I scroll up too soon, just let me know. We can leave some of that on the screen there. For the physical vector A dot B, we've defined everything so that we can know what the dot product is. Now, if we want to get the components, we can pick 3 physical vectors, I hat, j hat, and k hat, which are unit vectors in some direction. Key idea is that they have to be linearly independent or they're not a basis. And we're going to come back to that in detail, but it's nice to say it as many times as I can. So these are linearly independent. Now, they don't have to be orthogonal, but it's really nice if they're orthogonal, which we simply define as I hat dot j hat equals 0. Orthogonal means the dot product is 0, so I hat dot k hat is also 0, and then j hat dot k hat is 0. Once I have those unit vectors, I can project any vector onto each of them. So I can now define my components. So Cx would be C dot I hat. Cy would be C dot j hat. And Cz would be C dot k hat. Now, you've been using physical vectors your whole life, ever since you started doing anything in physics or math. And so developing this machinery might seem excessive at this point. However, you'll find once we get to abstract vectors, it's critical, because you won't have that same intuition and you'll have to rely on it. And one of the cool things that we've done in physics is introduced a really neat notation called the bra-ket notation. So if I was to write my vector C, I can write it as a row vector. I can write it in terms of I hat and j hat. But I can also write it in terms of things we call kets. These are kets. And they also come with their matching pair, the bra. And that makes, when I put them together, the bra-ket. And we'll see how long it takes for you to laugh. Right? The brackets, the bra-ket. Okay. Physicist humor isn't always the best. My daughter does complain that she can't stand the fact that her 8th grade science teacher is always making silly science jokes. But she goes, at least they're similar to yours, Dad, so I understand. So we've got, and this, I don't know why, this tends to cause students, how many of you have seen kets already? Yeah. You're going to see them all over quantum mechanics next year if you haven't seen them yet. And I don't know why it causes problems. It's just a notation. It is just a notation. It's no different than I hat. It's no different than this. And we're going to use them a lot in this class. The Boaz book doesn't really use them that much. I think she does mention them, but we're going to use them a lot. They're really, really critical to what we do.
Why is this a nice term?
This, okay, good question. I was going to save it for later, but I'll actually tell you now why it's nicer. A couple of things. First of all, this gets tedious and only makes sense when you're doing physical vectors, the I hat, j hat, k hat. This, you have no idea what your basis was, because there's no indication there. What this does is inside the ket, I get to put any label I want to remind me what my basis is. So if my vector space is apples, oranges, and grapes, I would have the basis A, G, and O for apples, oranges, and grapes. Now, I could write those as A hat, O hat, and J hat, but it gets confusing. The other thing is, and then it reminds us, see, these were designed for real number spaces. When you do complex numbers, which you have to do in quantum mechanics, The right way to do the dot product, which we'll do later, but is to make this number the complex conjugate. And the bracket notation has that built in. So you don't ever, you're less likely to make the mistake of forgetting the complex conjugate. Was that where you're going to come on? Yeah. And so it's those two things. It's building in the complex conjugate, and it's building in a way to label. And you also get to use bras and cats. And you get to say bracket. See? It makes you happy when you're doing your homework. I'm using a bracket. Now, again, without knowing that, it makes the following look tedious. So let's suppose I have V, which is Vx, whoops, I plus Vyj plus Vzk. And I have W, which is Wxi plus Wjj plus Wzk. Now, I've just said everything's orthonormal. So one of the other things that would often happen is I used ijk here. I might use the basis 1, 2, 3 for the set I, j, k. Now, this is slightly bad notation. Actually, I'll be a little bit better. So I could index these 3 as n, where n goes from 1 to 3. That's helpful a little bit notationally, because now I can write my basis is such that m, the scalar product, so this is now how I write dot products, or scalar products. I don't use a dot, I use my bracket. So this is replacing n dot m. Okay, this equals 1 if n equals m, and 0 if n is not equal to m. And we define this function as the delta function, delta nm. And we're going to use this over and over. So right now, if you don't quite get it yet, okay, we're going to use this a lot. But notice it's given me a shorthand notation to tell you something about my 3 basis vectors all at once. Because I'm indexing over 1, 2, 3. I don't have to write it 9 times. I just tell you right away, look, it's normalized. They're of unit magnitude because any vector times itself is 1. And they're orthogonal because any vector times a different vector is 0. So it's really cool shorthand notation. And having done that, I can now do v dot w, which in my new notation I write as vw, which if they were complex, I would do my complex conjugate like I should, but written out in longhand is just vx, going back to my old notation, I, plus vyj plus vzk, dotted into wxi plus wyj plus wzk. And now as you do all the multiplications, I've turned this into a problem of vector multiplying basis vectors. So I dotted into I, that's 1. I dotted into j, that's 0. I dotted into k, that's 0. And multiplying scalars, wx times vx. And because I've done it this way, I can take any abstract set of vectors, pick a basis, tell you how those basis vectors multiply. They may or may not be orthogonal or normalized, but as long as I have a rule on how to multiply all my basis vectors, I can now do this any way I want. And it really increases my options and flexibility. So in this case, it looks long, and if you work it through, you will get vxwx plus vywy plus vzwz. And I encourage you to do that as an exercise. But it really does kind of do what you want. And like I said, this is more prepping you for stuff that will come.